Thanks for being here today. Appreciate your attendance. In front of you, there is a USU water main break report that Utah State University has recently published. Feel free to peruse through it while I'm giving this presentation, because most of the slides that I'm showing here today are in the report, and you will want to study them more in depth. I'll be going through them rather quickly to give you an overview of some of our findings, and then feel free to ask any questions. So, yeah, thank you. The Utah State University water main break studies have now taken place 3 times, 2012, 2018, 2023. And in December of 2023 is when we finished this last report. And in each study, there was a basic and a detailed survey that was sent out to utilities all across the United States and Canada. In the basic survey, there was essentially 10 basic questions. In the detailed survey, more detailed, 20 of them. A basic survey, we ask utilities about system characteristics, asset management, pipe failure data, all kinds of information about the number of failures, typical cause of failures, the pipe material in which the failure occurred. But in the detailed survey, we asked more specific questions about the utility and pipe failures, specifically to size, pipe size, that the failures were occurring. And then we ask about target break rates. Do they have a defined target break rate when they replace their pipe, or the typical age of the pipe when it fails, or more about the soil and the corrosivity of the soil? It was there corrosion protection methods, and a little bit about construction failure. And then we asked some asset management questions also in the detailed survey. So in the 2012 report, we had 188 basic surveys that were provided back to us, and 47 detailed surveys. And those surveys in the basic survey represented 117,000 miles of pipe. In the 2018 study, there was 281 basic surveys and 98 detailed surveys. 170,000 miles of pipe was represented. And then in this most current study, 802 basic surveys, 172 detailed surveys, nearly 400,000 miles of pipe represented. And part of the reason I show this is just to represent the significance of this most current study, because we really did have a widespread and well-distributed representation of utilities across the US and Canada. Of those 802 basic surveys, 791 of them provided accurate miles of pipe that we could use to analyze the data, and 778 of them provided break rate data that we could utilize accurately. This is just a kind of an image to give you an idea of the significance of the 2018 study. There was nearly 40,000 report downloads across the world. And when the 2023 study went live online in February of this year, since then there's been almost 7,000 downloads. So it's of interest to people, and utilities are using this report as an asset management tool. And you'll be able to see why as we get into the report a little bit. This is just a simple graphic that shows the 3 basic surveys and kind of the significance of the number of respondents over here on the y-axis. The way we'd handled this study is we first started out by sending out a whole bunch of emails to utilities across the country. Nearly 7,500 utilities were contacted, and between March and December of 2022. asking them for information. And we had to give them a motivation or a reason to respond. And so one of the promises was that we would keep their data anonymous because they don't want to share break rate information and then publicize it to the world. And but we also promised them the report and information specific to their utility after we analyzed the information. A link was provided to the basic and detailed survey, and then our team at USU made lots and lots of phone calls and sent emails out to remind and motivate people to be involved. The data that was given back to us was given to us in a PDF formatted a format so that we could extract it directly to Excel. And then sometimes old school managers of utilities would just write it out on a piece of paper and hard mail it to us, so we had to actually type all the numbers back into our master spreadsheet. So there was lots of ways to gather the information. The objectives of this study, just quickly so you kind of understand what we're trying to focus on, we really wanted to capture as many responses as possible because we want, the more information you have, the better it is in terms of the sampling and what you can make sense out of it. As far as the responses, we wanted to understand trends. Now that we'd have a 2012, 2018, and then a current study, we knew that we could start to capture trends in the US and Canada. And this was something that we targeted in terms of how we asked the questions so we could evaluate trends. We wanted to look at smaller utilities and how they relate to larger utilities in terms of their break rates. We wanted to understand how pipes break as a function of diameter. We wanted to ensure accuracy. We just didn't want this slug of data to be dumped and then it really wasn't accurate. We were really careful about quality control and removing anomalous data and data that we knew was nonsensical. It was removed. And we wanted to get a uniform representation across the US and Canada so that we can see what's happening everywhere in North America. So here's a GIS geo-referenced map just to show you where we had respondents come from in this current study, and hopefully you can see the distribution and the representation, which we felt was really good. Obviously you can see the more urbanized areas where there's more responses because there's multiple utilities in those urbanized areas, not just one. There can be up to 30 or 40 utilities in some of these larger cities. In 2018, we were able to collect data from 48 of 50 states and 7 provinces. And then in this current study, we got all but 1 state and all of the Canadian provinces. This study was able to represent 30% of the population of the US and Canada and 17% of all of the pipe that's in the ground. So that's one of the reasons that we feel this is a significant study.
When you say 30% of the population,
the
mileage of the length of pipe?
So I'll show you how that works in just a minute, but essentially what that is when a utility provides to us information and their associated population, that population is related to what we know to be in the entire country. And so that's where we get that. This map is a report-based map that we developed. It shows how we broke up all of the data received into regions. And so I just want to show you this so that as we review plots and tables, and it has region numbers, you know where those regions are. So just quickly, Region 9 is Canada. Where we are now is in Region 7 down in the southeast. Region 1 is Alaska, Washington, Oregon, and Idaho. and so forth. And so as you look at region numbers and perhaps recognize variances from one region to the other, you can kind of see that some of it might be Midwest, Region 4, and the more rural or smaller utilities associated, or another thing might be Region 9 is because it's Toronto or Calgary and bigger cities. So just keep that in mind. And we'll review that again. So here's a summary of all of, and back to your question, a summary of all of the utilities that responded. Here we have region number, like we just looked at, and the number of respondents from each region. The miles of pipe from the basic survey that was represented, and the population represented in that from those 55 respondents, adding up to 112 million people and 399,000 miles of pipe represented from those 9 regions. The detailed survey, you can see a little bit different number and smaller numbers of respondents because there's more information, less utilities are interested in taking the time to fill it out. Most of the information here was for more developed, larger utilities because they have the resources to fill out the information. So just keep that in mind when we look at database information when we're relating basic survey and detailed survey. All sizes report here, more urbanized and larger utilities are reporting here. So here's a basic and detailed survey comparison just to show you the magnitude of respondents by region in the basic and detailed survey. I just showed some of these quickly so you can get a feel before we actually get into the actual data. That same plot I just showed you is now a line on this secondary y-axis representing number of respondents, and these bars represent the basic and detailed surveys in terms of miles of pipe. And so you can see very quickly Region 5 and Region 7 have the most miles of pipe represented. Region 1, the least amount of miles of pipe represented. As far as, and then the corresponding number of respondents that reported from those regions.
Was there any significance to grouping the regions as you did? Is it just by like geographical reason or temperature? Or like, I guess that's my question,
So is there any variance in the region from what?
Or yeah, like why did you group the regions in the way you did, and how does that reflect?
So we broke the regions out so you could see there's several states in the Northeast, several states in the Southeast. We had to break up the entire country in some manner so we could make sense out of it, and we kept states in certain blocks according to the area. Yes, temperature does have an effect on the data associated with those regions, but so does kind of the culture of that region. If you might imagine, some parts of the country are more inclined to use certain kinds of pipe and other parts of the country to use other kinds of pipe. And so some of that comes out in the report as we look at it more closely. Whoops. This is an example of the 3 reports from Utah State University and the associated miles of pipe that came from those reports. And so you can see obviously the current study has a tremendously larger amount of miles of pipe as compared to the previous studies.
Does that take into account, obviously your regions are different, like you said, with Toronto being a very populated area.
Yeah.
Does that compare to, let's just say, the volume in there too? Like it's linear footage or miles, but does it show the density of like what is going in there?
This is only reported miles of pipe.
Okay, gotcha.
So this is how many miles of pipe are represented in this study as reported from the respondents. So no, But some of the answer to your question is in the report in terms of density.
Right, population.
Uh-huh.
Comparison.
We have a slide here in just a minute of people per miles of pipe, and that'll show up here in just a minute. This particular one is just a report from the basic survey of the average miles of pipe represented from each of these regions. And so you can see Region 3, which happens to be Montana, Wyoming, Colorado, and Utah, reported from that region in this report was the smallest average miles of pipe for each of the utilities that reported. And correspondingly, Region 5, which is Texas and South Central parts of the United States, the highest average miles of pipe from each utility. And so again, in part to your question, and maybe some of the rest of you are wondering it yourself, you start to see the densities and the trends in terms of the data and where it comes from. The average miles of pipe reported in the entire study is 505 miles of pipe in each utility. And then backing up, that 505 average miles of pipe represents 146,000 average population, and that's this next slide. You can see over here on the right, this average population, where y-axis is population served from average population served from each utility that reported. And again, you can see, well, here's Region 6, which is the Great Lakes area, and Region 2, which is California and Nevada. You can see where the density populations are and the larger average populations from those utilities. We broke up the study into 4 utility sizes, 0 to 500 miles being the smallest, and very large utilities being over 3,000 miles. And part of the reason we did that is so we could start to look at and evaluate how there's different trends between utility sizes. So here on the x-axis, we have those 4 subgroups of utility sizes in terms of miles of pipe. The secondary y-axis is number of respondents, and the primary y-axis is miles of pipe. So a couple things I want you to capture immediately from this graphic is that this line, secondary y-axis, the number right here shows the number of respondents that actually responded in this subgroup of utility group size greater than 3,000. 22, 40, 135, 594. This trend in terms of the distribution of smaller utility sizes to larger utility sizes is reality. This is very consistent with how EPA reports the distribution of utility sizes in the country. And so another thing we notice here, and this is just my own observation, I think it's pure luck, is that this 100,000 approximately average of every utility size is just dumb luck in terms of what we received in this report. It's a nice distribution for every subset of utility size. This is the same graphic, but just presented differently in a pie-shaped form. You can see 2018, 2013, the 0 to 500 mile portion of the 2018 study was 68% of the total respondents, and in 2023, 75%. So we had a little more response from the smaller utility sizes, but essentially you can see the distributions are very similar. This is a plot that shows population served versus miles of pipe, and you can just see the scatter plot. It just gives your brain a way to capture where all the data comes from in terms of population served and miles of pipe. This is population served per mile of pipe, back to your question, it helps you understand in terms of where the denser populations are in terms of the number of miles of pipe. And so immediately you can see here Region 9, which is Canada. We know those are larger cities in the southern provinces of Canada. And Region 4, which is the Midwest states, which has a lot smaller population per miles of pipe. And that makes sense because you gotta run a lot of pipe to get from one farm to the next. And so that number we do know would be a smaller number. And where you're in very highly dense populated cities, you have a lot of people on a mile of pipe. So this is another way you can start to see and understand how this data try to make sense of it for yourself. This particular table goes back to how we calculated this 30% and this 17% that I referred to earlier. This upper tier up here, these 3 rows, represent references from EPA, US Census Bureau, and Statistics Canada of what the population actually is in the US and Canada. 373 million people are in the US and Canada from these references, and 2.333 million miles of pipe are in the ground according to these references. And so using that information and the associated, the second horizontal tier, using this 112 million people that we know are represented in this study and the 399,000 miles of pipe represented in this study, this divided by this is 17%. And this divided by this is 30%. And so that's where we get those numbers. Just a quick review of acronyms for this study. I think most of you are familiar with these acronyms, but asbestos cement, AC, CI cast iron, CSC, concrete steel cylinder, DI ductile iron, HDPE, PVC, PVCO, and steel. So as we refer to these pipe materials moving forward now, we'll just be using these acronyms. So here the acronyms are shown here on the x-axis. Y-axis is miles of pipe provided to us from the basic survey. And you can see immediately the prominence of 4 different pipe materials represented in this study: PVC, ductile iron, cast iron, and asbestos cement. And you can also see the other materials and their insignificance in terms of the overall distribution from this study. And we believe it's not just the study, we believe that's reality, that's what's out there. And so you can kind of get the idea. This same plot shown in percentages of pipe length according to total percentages. If you add up all these percentages, it adds up to 100%. So this 29.1% is of all the pipe we received information about. 29.1% of it is PVC. And it helps you to see, you understand that 0.6% of it is HDPE, get a feel for how much actually is in the ground out there. This is a percentage of pipe lengths of most common materials from the last report we did in 2018 and the current study. And you can see there, for the 4 prominent pipe materials that we just talked about, if you look at if you add up this number, 12.7 and 28.4, AC and CI is 41% for 2018. If you add up this number and this number for the current study, it's 33%. So there's a reduction of 7.8% in these two pipe materials since 2015. However, there's an increase in PVC of 7%, which seems to correspond to this reduction. Now, the reason I point this out is because AC and CI pipe are They haven't been manufactured for 30 years. And so utilities, when they replace certain materials, they're replacing it with something. And it appears one of the products that's being used to replace it is PVC from the report. Again, I'll just show you this graphic again, not because I need to see it, but I want you to see it. Just to familiarize yourself with where these regions are in the report. All right, this appears, and I know you won't be able to read all this, but you can see it in the report if you wanted to just parallel it. This is pipe material usage as a percentage of total length by region. And to help you interpret this plot, there's a lot of information here, but it's valuable information. Let's start here. If you add up all values for each region, it equals 100%. So let's just take region 1. If you add up all those percentages in region 1, it adds up to 100%. So now let's look at this example. 48% of all pipe in region 4 is PVC. So you go to region 4, you look at this 48%. Of all the pipe in region 4, 48% of it is PVC. And that's how you can interpret by region the distribution of pipe materials. If you look at prominence in region, this is a 2012 map of the pipe material that was most prominent in the 2012 study. And it's color-coded according to material. So here's the legend up here. Blue, PVC, this brown color is cast iron, the black, ductile iron, this yellow color is asbestos cement. And the pie shape next to each region represents the distribution of all the pipe materials for that region. And you can see this one, this region 1 is brown. That is the biggest pie shape on that pie, or the largest color component on that pie, and so that's why the map itself is colored brown. So if you go through 2018, you can start to see color differences. And if you go to 2023, you start to see additional color differences. And if you put them all together, it becomes clear some of the trends in pipe material prominence that's occurring across the country. I noted down here, just for your reference, region 3, 4, 5, 7, and 9 are trending towards PVC as you go from left to right. Regions 1 and 6 are trending towards ductile iron. And asbestos cement remains the most common pipe material in region 2, and cast iron in region 8. And so this is a fun, is that the right word? This is an enlightening way to illustrate the prominence and the trends of pipe materials across time. I guess it's fun, right?
For
Yeah.
regions 1 and 6, what is the reason, they are trending towards the ductile iron?
So I'm sorry,
Like, you know number 2?
region 2?
Region 1 and 6, they are trending towards the use of ductile iron.
Oh, this is region, so it's because ductile iron, region 1 and region 6.
So what is the reason? They are trending?
What is the reason?
Yeah,
So our report does not say the why,
yeah,
it only says the what.
correct.
I don't know.
Because we understand.
It could be, some of it could be the trends that the companies and the utilities like ductile iron, and so they'll use it.
Okay.
Yeah. Some of it might be that they're set up to use ductile iron, and they have a sales train of ductile iron purchases, and they don't want to mess with changing it. I don't know, but our report did not cover the why.
So like that,
in the Great Lakes region, they have a tendency to bury their pipe deeper.
Yeah.
And so the pipe can be safer
Yeah.
in terms of the effects of temperature and corrosion and other things. And so, yeah, there might be reasons like that, but our report did not cover the why of, yeah.
You'll see some trends in the report later that
Yeah.
sort of say that it's not burial depth.
Oh,
Because Canada switched to PVC, they bury it deeper,
Oh, okay.
and they actually have the lowest break rates
okay.
of all.
But what he's saying is correct. Some of it could be in terms of the safety of the pipe, in terms of how it's buried, but whether it's region 8, 6, 5, or 2, we don't know. We didn't capture any of that information. Yeah.
We are in Florida, so we know Florida, it's trending towards PVC.
Yes,
For
clearly.
the reason, okay?
Clearly.
Easier to.
Yeah. No, exactly right. Yes.
Is it illustrating the replacement as well, or is it just the new material?
Both.
Okay.
Both. As new subdivisions and other things develop, it would include that, but it also include the use of the replacement pipe too. Yeah, thank you. Yes.
Okay, so bear with me. But what I'm seeing then in California, and what is that, Nevada, that they're still using asbestos, or that just means they haven't replaced it?
The second. They have not replaced it. In terms of what you say, I have to clarify. Whether they're still using it, we know they're not still installing it because asbestos cement pipe has not been manufactured for 30 years. So it's in the ground, it's still in the ground, and the utility reported it as being still in the ground. And so eventually it will be replaced because it'll come to the end of its useful life and it will be replaced with something. But in terms of this 10-year period, it has not yet. Does that make sense?
Yeah.
Does that answer your question? Okay. All right, this is a pipe age distribution chart that shows from the detailed survey how the different, how all of the pipe that was represented in the detailed survey breaks out in terms of how old it is. And so you can see that over 75% of all the pipe that was reported to us is greater than 20 years old, all those sections. And just to relate, in 2018, that this greater than 50 years section was 28%, and now it's 32.9%, which might be an indication that our buried pipe infrastructure is aging. I think everyone would agree with that. This particular graphic, if we look at the legend first, this shows the distribution from the detailed survey by percentage of all the pipe that was represented in the detailed survey. So 33.8% of it was ductile iron, 20% was PVC, and HDPE had 0.5%. This down here is how that individual pipe material is distributed by age. So the easiest way to understand it is to say, okay, although we only had 0.5% of the total pipe from the detailed survey was HDPE, but you can see that 0.5% how it's distributed by age. And so you can see the 30 to 40 year, the 20, the 10 to 20, and the 0 to 10. So let's just look at some examples. 23% of PVC is 0 to 10 years old, and 2% is greater than 50 years old. 86% of cast iron, that's this guy, is cast iron is over 50 years old, and 41%, that's this one right here, is over 50 years old. And so you can easily see how each pipe material individually is distributed by age. One thing to point out is you won't see any gold or brown in the last 30 years. We already know it hasn't been manufactured, AC and CI pipe, but it's being reported as such too. Nobody's installing AC and CI pipe because They didn't buy it. So it was put in the ground back here. Back to your question about Region 2, it's still in the ground, but no new AC and CI pipes been installed. This is a age distribution graphic that shows how all the pipe is distributed by age. I mean, one of the things we need to just help you understand is that if you add up all these percentages, it adds up to 100%. So all these percentages add up to 100%. So the example to help you understand how this plot works is 21.1% of all pipe is cast iron pipe that's over 50 years old. So now you can see where everything is weighted in terms of age and material. This is pipe diameter plot that shows 3 to 8 inch, 10 to 12 inch pipe, and so forth up to the larger pipe sizes. And this is percentage of total pipe length from the detailed survey. And if you add up these two guys right here, that's 86% of all the pipe reported to us is 12 inch and smaller. And that also helps us understand, okay, now we're talking about smaller pipe sizes and not all the big ones. Most of the pipe represented in the country, in Canada, but also in this report is these smaller 12 inch to down to 3 inch pipe sizes. Interestingly, in the 2018 USU report, this was 67% and this one was 18%, so almost identical in terms of the distribution of pipe represented. This graphic shows percentage of length of each pipe material. And so if you add up all values for a given material, it adds up to 100%. So any like this yellow one here, it's this 67%. If you add up all the yellows, it adds up to 100%. So let's look at the example of how to understand this graph. 79.4% of all AC pipe, 79.4% of all AC pipe, that's this guy right here, is 3 to 8 inches in diameter. So you start to see, okay, how is the asbestos cement pipe broken up in terms of size? That's what you can learn from this graphic. And this is very similar, but this is adding up all values. So it's an accumulative percentage. 22% of all pipe, that's this one right here we're looking at, this black one. 22% of all pipe in all sizes is 3 to 8 inch ductile iron. So now you can see a weighted distribution in terms of all the pipe in terms of percentage. And quickly you can see that these transmission pipe sizes, although they're important to a utility, that's not where most of the pipe is. And I think everyone knows that, but graphically it really jumps out when you start to look at, okay, most of our pipe is down here in these smaller sizes. We asked questions about average and maximum pressure in their system. These were generic questions, so there wasn't any detail in terms of whether it was transmission or distribution pipe sizes, but the maximum pressure reported was 120, average 71. And in 2018, those same numbers were 69 and 119, so almost identical in terms of pressure distributions. We did also ask a question about what their calculated or measured water loss is to leakage, and the average response from all basic survey respondents was 11%. And that might be consistent with something you're familiar with in terms of as you work with utilities, that's on water audits, that's a common number. This is a distribution of average and maximum water demand by population. The teal is maximum, the darker blue is average million gallons per day. Population here, million gallons per day on the y-axis, and you can see the distribution in terms of water demand. The average water demand was reported to be 143 gallons per day per person from our study. Now let's get into pipe failures. These are the questions we actually ask in the surveys to the utility. Consider a water main failure as one where leakage was detected and repairs were made. However, do not report joint leakage or failures due to construction damage or tapping of service lines because these failures are not indicative of pipe degradation. Our report was striving to understand material degradation and not necessarily including all of the other things that can happen in terms of leakage and damage. And so that's why we ask it in this way. Only include water supply mains, do not include sewer or force main data or service lines or lines less than 3 inches in diameter. So we try to put an envelope on what they're reporting on and also be a little more specific on what we're trying to capture. So this is a 12-month period from the basic survey. This is break rate on the y-axis, which is breaks per 100 miles per year. Breaks per 100 miles per year. And common pipe materials down here. And you can immediately see cast iron has a relatively high break rate of 28.6. PVC has a low break rate of 2.9, and this is pipe material. This is a 5-year period. The same graph I just showed you is plotted on here in the 12-month, but it's compared to the 5-year. And you can see that whether it's 5 years or 1 year, the break rates are relatively consistent in terms of magnitude, but also as compared to their neighbor pipe materials. This is a comparison of three USU studies, 2012, 2018, 2023. And again, you can see the relative consistency in the break rates as you compare pipe materials and within that pipe material. This data table shows 2012 in this column, 2018 break rates in this column, and 2023 break rates in this column, and the corresponding numbers used to calculate the 2023 break rates and the material that we were comparing. This number right here is the overall break rate calculated for this 2023 study from the basic survey, 11.1. If you apply 11.1 breaks per 100 miles per year to that 2.333 million miles of pipe that we know are in the ground from the EPA reference, that equates to 260,000 water main breaks that are occurring annually. We're trying to make some sense out of these numbers now. And if you apply a $10,000 factor, and we know it could be a $3,000 or it could be $50,000 factor to repair a water main break, but we just put a $10,000 factor on there. This is a $2.6 billion annual cost just to repair breaks that are occurring in the US and Canada. And so we're trying to put some economic value to these numbers so it makes sense in terms of what we're actually seeing. This decrease from 14 in 2018 to 11, it may be, we don't know for sure, but we suppose it may be a reduced inventory of those pipe materials that have the highest break rates. So you think about it, if you have a whole bunch of cast iron that has a 28.6 breaks per 100 miles per year break rate, and over time you're replacing some of it with a material that has a lower break rate, then your overall break rates are going to reduce. Yeah?
Does this, when they report their break per year, do they happen to also report the age of the pipe?
Yes, if it's a detailed survey. Yeah.
Does this
This is the basic survey here.
Okay, all right.
So it would not have included age or diameter.
Do
I think I have a slide here. I can show you some comparisons of the break rates. This is, and I'll try to point out what we're looking at. Here's the basic survey. This graphic shows the 11, the 14, the 11 overall break rates in terms of this teal bars and the miles of pipe represented from the basic survey in the survey year. One of the questions that we asked that I think is important to just point out for your reference is, do you have a target break rate at which pipe replacement is implemented? That's what the utilities were asked. And the average response was 21 breaks per 100 miles per year. So to help you understand what that means, essentially a utility in their asset management plan may have a target break rate. If we ever reach 21 or higher, we really need to replace that pipe. And so that's just of interest. This, from the basic survey in 2018 and 2023, the same 151 utilities that reported in both USU studies, break rates per 100 miles per year and material. And we find it interesting that there's a very good correlation in terms of break rates from year to year and also between materials. But one thing that's interesting, you know, the fact that they reported in 2018 may have placed a little more focus on their own pipes and the break rates they had, because look at every one of these pipe materials is lower in this study than the previous study for the same utilities. I don't know the reason for why it's lower, but I wonder if it's because they just put a little more care into it because we asked the questions and they thought about it. It makes sense anyway. This question? This is the same 20 utilities for all three studies, and that same correlation's not there for that earlier study, but some of it might be just the amount of data that we received in the last two studies is a lot more than that first study, so it might be a sampling error. But you can see the same correlations in terms of magnitude and a relative difference between materials for all three studies. Now, utility size in the basic survey, a 12-month period. Here's utility size, those four sizes that we talked about earlier. And we were trying to capture whether or not the utility size would have some effect on the number of break rates. You know, we surmised, or we supposed, that smaller utilities, maybe there's only one or two managers of the system, they would have higher break rates because they just don't have the resources to care for their system, but we found zero correlation. And so it points the finger less to people and more to material in terms of utility size. And so just another thing we can capture, this weird thing right here, we think is galvanized pipe. It's just something's going on there, and I think it probably was reported as galvanized pipe, and we weren't very clear to keep that out of there. But you can see the shape, the fingerprint of each utility size is almost identical. If you look at the 5-year period, it's the same. Essentially, there's really no correlation higher or lower as you change utility size. Now, this is an interesting graphic because it shows Canada and the US in terms of these common pipe materials and their break rates. And you'll see immediately cast iron and ductile iron reported a much higher break rate in Canada than they did in the US. And again, we don't know the why of this perfectly, but we're supposing that some of it might have to do with Canada has some very highly corrosive soils. You're going to hear a little more about that from a Canadian here in just a minute. But it could be that, or it could be just the extreme temperatures. We're not sure, but as reported, that's an interesting data point. This is break rate by diameter of pipe material from the detailed survey. And back to your question about detailed versus basic. Diameter, you'll notice one of the interesting things is there seems to be a increased trend in break rate as you get smaller diameter. And if we move to the next slide where we zoom in on these three smaller ones, these smaller size ranges of pipes, clearly there's a trend where the break rate increases as you get smaller and smaller sizes. Some of that may have to do with the amount of pipe that you're reporting, but there is a correlation. So just a reminder that 86% of all the pipe reported in the detailed survey was in this 3 to 12 inch range. So that's where the majority of the pipe is. This is that 3 to 12 inch range from the detailed survey, and you can see the overall breaks per 100 miles per year for these common pipe materials, cast iron being 32.5, PVC 3. And again, this is a 3 to 8 inch pipe range, which has the largest amount of pipe associated with that range of pipe. Same correlation, same break rate from the detailed survey. I just point out that the difference between this PVC and this cast iron is 11 times, and it's almost 2 times just ductile iron to PVC. So there is quite some significant differences in terms of pipe material sustainability or pipe material able to resist breaks. This is a table that we broke out transmission pipe sizes greater than 14 inch and distribution pipe sizes 3 to 12 inch in terms of these common pipe materials and their break rates. And you can immediately see the overall break rate of 2.2 right here for transmission sizes, 13.3 for distribution sizes, and a 505% increase, which is 6 times difference between these two sizes. There's a couple indications of something that's happening here. Obviously, if you're managing a transmission line, you're going to take really good care to install it, to maintain it, to inspect it. It's your cash register for the whole system. When that goes down, the whole system goes down, right? And not to say that we don't care about these, but this is where people are putting a lot more energy into caring for their materials. That could be one of the reasons, and I suppose that most of you would agree with that. We ask about common failure modes. Here's how it was reported for how pipes fail. Circumferential crack and corrosion being the most common failure modes. We ask about corrosion prevention methods, polywrap and cathodic protection being the most common in terms of how iron-based pipes are protected. Down here, I have a note here, 75% of utilities surveyed reported one or more areas in their system that have corrosive soil conditions, and 73% reported some kind of corrosion protection that's used in their system. Now, getting into corrosion and corrosion protection, let's just show you a few slides. This is a USDA soil survey database. It's online. We pulled it. It shows green, yellow, and red being the most corrosive soils in the country, and green being the location of the least corrosive soils. In our study, in this current USU study, we applied this graphic using ArcGIS and the colored pixels to quantify in terms of 1 being green, yellow being 2, red being a number 3, to quantify every single county in which a utility was located. So this is a county in Nebraska, just to show you an example. We found the boundary of the county. We used ArcGIS to then quantify the soil corrosion index is what we called it, based on a 1, 2, and 3 and the number of colored pixels in that county. And in so doing, we came up with a range of corrosion indices. These are equal width ranges, and the number of utilities associated with each of those corrosion index ranges. And you can see here's the average corrosion index for the US, and those utilities that are higher and lower. But we can't analyze the data very well if the number of respondents is not equal. So we weighted the data by making an approximately equal number of utilities by changing the range of the corrosion index range. And then we looked at cast iron and ductile iron in terms of their overall corrosion index, and cast iron and ductile iron in terms of their break rates for those number of utilities. And then we plotted it. So now we have a weighted sample set, each dot representing approximately the same number of utilities. And you can see a trend. So here's corrosion index on the x-axis. Here's a 3, meaning highly corrosive soils, 2, medium, and 1 being low corrosive soils. And you can see right here, this 3 down to a 1, that's approximately 2.5 times more breaks with highly corrosive soils than low corrosive soils. That's what we can capture out of this graphic. Same for ductile iron. We can see that there's over 6 times the break rate of ductile iron pipe in highly corrosive soils as opposed to low corrosive soils down here where the intersect is. And a fairly good R-squared for this linear regression. This particular plot, just to change the subject here, is construction-related failures. To interpret this, let's look at this hashed legend right here. This is the percentage of pipe installed in the last 10 years. So you can see the hashed bars represent the percentage of pipe installed in the last 10 years, where all the hash bars added up adds up to 100%. So 50 and 42% of all the pipe from the detailed survey, PVC and ductile iron, that's where the pipe was installed in the last 10 years, and the associated number of construction failures. And so if you read this note, whenever the hash bar is higher than the solid bar, it indicates that the material has a comparatively lower construction-related damage.
What is the definition of construction failure?
A construction failure is at the time that it's being installed or soon thereafter if there is a leak.
Maybe like an over-insertion?
Yeah, so a construction failure can be a myriad of things, from the backhoe hitting the pipe or damaging it because you dropped it, or a rock impinging into the pipe. All of that is a construction failure that's not material related in terms of what we're trying to capture here in this report. This table, here's some questions we asked that are of interest to you, I think. Average age of failing water mains. What is the average age of your failing water mains? And it was reported 53 years. That was the average response. And just keep that in mind, that number. What is your average expected life of a new water main when you install it? How long do you expect that it's going to last? 78 years. So there's a discrepancy here already in terms of, okay, they're lasting 53, but we expect they're going to last 78. What is the percentage of, how many utilities actually have a pipe replacement program from the basic survey? 70%. And from the detailed survey, same question, 69%. So this means that about 30% of all the utilities that responded don't have a pipe replacement program. They probably just respond when they have to. And average percentage of water mains beyond their useful life, but there's not funding to replace it. So another way to ask that question, how much of the pipe in your system would you replace because you know you need to, but you just don't have the money to replace it. And it's 20% of our system needs to be replaced, but we don't have money to replace it. So now let's get into what we learned from this. In 2012, 2018, the average age of failing water mains was reported to be 47 and 50 years respectively. This study, 53 years. So an aging infrastructure. The average age of failing water mains is 53 years, but 33%, this is 33%, of the 2.33 million miles of pipe that we know is in the ground are greater than 50 years old. That's 770,000 miles of pipe. You start to get a feel for the magnitude of what we're dealing with in terms of the aging infrastructure. And if you apply this 19.4, this is the percentage of pipe that's out there that needs to be replaced, but there's no money to replace it. And if you apply that to the 2.33 million miles of pipe, that's 452,000 miles of pipe. And if you put a quantified economic value of about $1 million per mile of pipe, that's $452 billion shortfall that we need that much money to replace what needs to be replaced. So hopefully you can see that you can quantify some of these things. Just a few more slides. These are questions we ask about what is allowed in terms of pipe material. And so if you look at the, let's look at the hash bars again first. This is percentage of pipe installed in the last 10 years, like the last one. You can see, let's just look at HDPE, might be an easy one to understand. In the last 10 years, 2.5% of all the pipe from the detailed survey installed was HDPE. But 66% of all utilities allow its use. So it kind of helps you understand, okay, we would allow the use of HDPE, but we're really not installing it. That's kind of what you can learn from this. This is the three studies from the detailed survey showing percentage of utilities and material that's allowed. And so you can see cast concrete steel cylinder, ductile iron, PVC, and steel. The percentage of utilities that approve ductile iron appears to be decreasing, and the and approval of steel has increased, and CSC and PVC relatively the same. Question about asset management questions. Do you use GIS? Nearly 90% of utilities said they have some kind of GIS system. Do you have smart technologies? In terms of digital technologies for your asset management, smart metering and pressure management being the most common. This particular graphic is a summary of some of the things we've just talked about that we've found significant from the study. Again, 17.1% of all the pipe in US and Canada is represented in this study. The average age of failing water mains is 53 years old, and we know that there's 770,000 miles of pipe that's over 50 years old. This 260,000 water main breaks that are occurring annually, that equates to $2.6 billion. And then in all three studies, we consistently saw that cast iron had the highest break rates and PVC had the lowest break rates in terms of pipe material. This is the final slide. This pie here comes from an EPA source, and I brought this on here to show the significance economically of how EPA feels our buried infrastructure is faring. This is a total 20-year need. And if you look at this dark zone here, this is distribution and transmission water lines. There's a $420 billion need in the next 20 years for this part of the infrastructure. Significant. That's what we're talking about in this report. And then to bring you back again to this 19.4% that we talked about earlier, and this $452 billion shortfall, although this is apples and this is oranges, it's the same, it's almost identical in terms of the value. And so although it might be a different report, it's probably the same pipe that's being reported about. And it's another indication that we feel there's some validity in terms of the significance of this report. It's how we've quantified it. That's it for my presentation. Thank you for your time today.